we have the problem y prime is equal to x plus y minus 3 squared minus 2 times x plus y minus 3. In this case, we need to have a substitution, so we will let v is equals to x plus y. Then from this substitution, we can get the value of dy over dx by getting the derivative both sides. So we have dv over dx is equal to 1 plus dy over dx. Then we have our dy over dx. dy over dx is equal to dv over dx minus 1. Then now that we have the value of our dy over dx, we can now substitute it to our y prime. So we have here dv over dx minus 1 is equal to x plus y is equal to v. So we will replace it with v equal to v minus 3 squared minus 2 times v minus 3. Now that we have that value, we need to simplify it further so that it would be easier for us to integrate it later. So we have dv over dx minus 1 is equal to, at this moment we'll factor out v minus 3 because it is common to both factors. So we have v minus 3 times v minus 3 minus 2. So simplifying this, we get dv over dx minus 1 is equal to v minus 3 times v minus 5. And then after getting this, we will transfer negative 1 on the other side, and we will operate this operation here, v minus 3 times v minus 5. So we will get, here we will get dv over dx is equal to v minus 3 times v minus 5 is equal to v squared minus 8v plus 15. Then we have the 1, so we will add it, transferring it to the other side will become positive. So we have now our dv over dx is equal to v squared minus 8v plus 16, or simply we can write this as dv over dx is equal to v minus 4 squared. Then multiplying both sides by dx and dividing it by v minus 4 squared, so we have dx times squared. So now we have dv over v minus 4 squared is equal to dx. as you can see here, we have a separable differential equation, so we just separate like terms, and then now at this moment we cannot proceed to integrating both sides, getting the derivative both sides. So we have this. So integrating this, we get negative 1 over v minus 4 equal to x. Then getting v from this, we get negative 1 is equal to vx. Oh, there is c here. Forgot, there is still c here, because when integrating we should have a constant, so c is an arbitrary constant. So let's proceed. So we have negative 1 equals to vx minus 4x plus vc minus 4c. There, minus 4c. And now we have that minus 4c. Then after that we can now get our vx from that. So we have from this we will separate like terms, those with v. So transferring it on the other side and factoring v out of it, we will get vx plus vc is equal to 4x plus 4c minus 1. So we can get v out of here, so we have v times x plus c is equal to 4x plus 4c minus 1. So getting v, we have v is equal to 4x plus 4c minus 1 over x plus c. Now that we have the value of v, we can now substitute back x plus y. If you recall, a while ago we have v is equals to x plus y, so we can substitute it in this equation. So we have x plus y is equal to 4x plus 4c minus 1 over x plus c. And getting y from there, we get y is equal to negative x plus 4x plus 4c minus 1 over x plus c. And this is our final solution for the problem, for our problem y prime equals x plus y minus 3 squared minus 2 times x plus y minus 3. Now we have the problem cotangent x times the second derivative of y plus first derivative of y plus 1 is equal to 0. First, we need to transform this into the form cotangent x times the second derivative of y plus first derivative of dy dx plus 1 is equal to 0. Then in this case we have a second order derivatives, but we can have a substitution here so that our equation will turn into a first order differential equation. So we have y prime equals to v, or dy over dx is equals to v. Then getting its second derivative, we have the second derivative of y, we have second derivative of y is equal to dv over dx. Then after getting that, we can now substitute it to our original equation. So we have cotangent x times dv over dx plus v plus 1 is equal to 0. Then transfer v plus 1 to the other side. So we have cotangent x dv over dx is equal to negative v plus 1. As you notice, we have a separable differential equation here, so we can just multiply both sides of the equation by dx and divide it by cotangent x and times negative v plus 1. Then after doing that, we have this equation dv over negative v plus 1 is equal to dx over cotangent x. And recall that we have our identity 1 over cotangent x is equal to tangent x. So we can just rewrite the left side of the equation as tangent x times tangent x dx. So we have now dv over negative v plus 1 is equal to tangent x dx. So now we can now integrate both sides of the equation. Integrating this, we get negative ln of v plus 1 equal to ln of second x plus c, where c is an arbitrary constant. And recall again from our identities, we have second x equal to 1 over cosine x, which is also equal to cosine x raised to the power of negative 1. So we can write this ln second x as ln cosine x raised to the power of negative 1, or negative ln cosine x. So we have here in the left side negative ln cosine x plus c. Then multiply both sides by negative 1 to get ln v plus 1 is equal to ln cosine x minus c. Then simplifying this, we have v plus 1 is equal to cosine x minus e to the c, and we'll let negative e to the c as our c1. Then we will get v from here. So we have v is equal to cosine x plus c1 minus 1, and let c1 minus 1 as our c2. So we have v is equal to cosine x plus c2. Then substituting the value of v, which is our y prime or dy over dx, we have dy over dx is equal to cosine x plus c2. Then our solution does not end here because we still don't have the value of y. So what we need to do here is we can just integrate both sides, because since this is a separable differential equation, so we will have now dy over dx, integrate this, is equal to cosine x plus c2. Integrating this, we have now y is equal to, integrating this in terms of x, y is equal to sine x plus c2x plus c3. And this is the solution of our differential equation. This is now our final. Now to check our results, if it is correct. So we have our checking. We have our answer, y is equals to sine x plus c2x plus c3. So we have our y prime equals cosine x plus c2, and the second derivative of y is equals to negative sine x plus c2. So after we have this, let's substitute it to our original equation, which is cotangent x times second derivative of y plus first derivative of y plus 1 is equals to 0. So we have now cotangent x equals to cosine over sine x times negative, the second derivative of y is negative sine x, plus first derivative of y, which is cosine x plus c2 plus 1 is equals to 0. So cancel this, and there remains negative cosine x plus cosine x plus c2 plus 1 is equals to 0. So this will cancel out, will become 0. So we have c2 equals negative 1. Then since we got c2, we need to substitute it back to our original equation. Cotangent x times second derivative of y plus first derivative of y plus 1 if it really holds true. So we have cotangent x is cosine x plus sine x times negative sine x plus cosine x plus c2, which is negative 1 plus 1 is equals to 0. Cancel, and negative 1 plus 1 equals to 0. So we have the remaining negative cosine x plus cosine x is equals to 0. Which means this on the left side of the equation is equals to 0. So 0 equals to 0. Since the right and left side of the equation are equal, so we can confirm that our solution y is equal to sine x plus c2x plus c3 satisfies our differential equation. Now we have the problem y prime plus y is equals to e to the power of x and we have initial value problem where y when x is 0 is equals to 2. Then as you notice, this is a linear equation. First we write this as dy over dx plus y is equal to e to the power of x, and our integrating factor here, we have no x here, so we have our integrating factor as v is equal to e to the power of integral of dx. So we have v is equal to the power of e to the power of x. Then after getting the integrating factor, we multiply both sides with e to the x, which is v. So then after we multiply this, we will get v times e to the xy equals to e to the 2x. Then we can now integrate both sides. So we have e to the xy equals 1/2 e to the 2x plus c, where c is an arbitrary constant. So dividing both sides by e to the power of x so that we can get y. So we have y equals 1/2 e to the 2x plus c over e to the x. So we have y equals, this will become 1/2 e to the power of x, so 1/2 e to the power of x and c plus c over e to the power of x. And this is now our solution. This is now the solution of the differential equation. Then after doing this, we will substitute the value of y when x is equals to 0, which is equals to 2. So we have our y is equals to 2. So we have 2 equals to 1/2 e to the power of 0, since we have this, since the value of our y is 2 when x is equal to 0, plus c over e to the power of 0, and e to the power of 0 is 1. So we have 2 equals to 1/2 plus c. So we have c equals 3/2. And now that we get our c, we can now substitute this to our solution, which is y equals 1/2 e to the power of x plus c to the power of c over e to the power of x. So we have y is equal to 1/2 e to the power of x, y equals to 1/2 e to the power of x plus 3/2 over e to the power of x, or we can write this as y is equal to 1/2 e to the power of x plus 3/2 e to the power of negative x. And this is our final answer. Now, checking our solution, we got y is equals to 1/2 e to the power of x plus 3/2 e to the power of negative x. So first we need to get its derivative, so y prime is equals to 1/2 e to the power of x minus 3/2 e to the power of negative x. So getting this, substitute this to our original equation, which is y prime plus y equals e to the power of x. So we have y prime equals to 1/2 e to the power of x minus 3/2 e to the power of negative x, and plus y, which is 1/2 e to the power of x plus 3/2 e to the power of negative x equals to e to the power of x. So now this will become 0. So we have the remaining 1/2 e to the power of x plus 1/2 e to the power of x equals to e to the power of x. So e to the power of x, 1/2 plus e to the power of x plus 1/2 e to the power of x is e to the power of x. So the left side of the equation bears e to the power of x equals to e to the power of x, which is correct. So our solution, y equals 1/2 e to the power of x plus 3/2 e to the power of negative x, holds true for our differential equation. Now we have the problem dy over dx equals x minus y over x plus 3y. As you notice in this problem, it seems like it is a homogeneous differential equation. So in order to confirm it, first we will let x equals to xt and y equals to yt. Then in order to do this, we will separate, we will have x plus 3y dy equals x minus y dx. Then we substitute the value xt and yt. So we have xt plus 3yt dy equals xt minus yt dx. Then we factor out t. We have t times x plus 3y dy equals t times x minus y dx. As you can see, on both sides of the equation we have the common factor t, so we can conclude that it is a homogeneous differential equation. So after this we will have y, so we will proceed to our substitution. We will let y equals to ux. Getting its derivative, we have dy equals to u dx plus x du. Then after that we will substitute this term to dy and this term to our y. We will substitute it to our equation x plus 3y dy equals x minus y dx. So we have now, x plus 3y, which is 3ux, will become 3ux, and then dy will substitute u dx plus x du. Then to the other side we have x minus y. Since our y is equals to ux, so we substitute it dx. Then we will perform the operations here, so we will have x u dx plus x squared du plus 3u squared dx plus 3u x squared du equals to distribute dx x dx minus ux dx. Then after having that equation, we will separate those terms with du to the other side and those with dx to the other side. We will group the terms. So we will have here x squared du plus 3u x squared du, 3u x squared du equals to x dx minus ux dx. Then transferring these terms with dx on the right side, we will have minus x u dx minus 3u squared du. So we have that, and then we will factor out the common terms, which is x squared and du. So we will have here x squared times 1 plus 3u du equals to, here the common factor is x and dx, so we have x times 1, and these terms are similar, so we will combine it, so it will become minus 2ux. Then here is this term here has x. Sorry for that. We have here x. So x minus 1 2ux minus 3u squared dx. Then we will divide both sides with x squared, so we have 1 plus 3u du is equal to 1 minus 2ux minus 3u squared dx over x. Then after doing that, we have attained a separable differential equation. So after doing that, we will divide both terms by 1 minus 2u, no x here, there's no x here, so we'll divide both terms by 1 minus 2u minus 3u squared. So we will have 1 plus 3u du over 1 minus 2u minus 3u squared. The other side we have dx over x. At this moment, we can now integrate both terms. As you can see, this is a partial. We can integrate this using partial fractions. So we have 1 plus 3u du, and the factor of this are negative 3u plus 1 times u plus 1. Is equal to, let's integrate this ln x plus c. So after getting that, so our problem here is how to get the derivative of this, so we will use partial fraction. Okay, we will first have a separate solution in getting this in integrating this, and we'll substitute it back later. So we have integral 4. So how can we integrate this? this is the integral. So we will have we're going to substitute this to our equation a while ago, which is integral of so now we will have negative 1/2 ln of negative 2u plus 1 times u plus 1 of ln x plus c. And we can write this as negative 1/2 ln negative 2u squared minus 2u plus 1 is equal to ln x, then ln of e to the power of c. So we will have, and we can now simplify this further, so we will have we will let e to the c, there's a plus there, e to the c equals to c1. So we will have ln c1 x. Then simplifying this further, we will get, since it's negative, so this will become as the properties of natural logarithms. So we will have here 3u squared minus 2u plus 1 to the power of negative 1/2. Then this is equals to c1x. So we will write this as 1 over square root of 3u squared minus 2u plus 1. So it is equals to c1x. Then so that we can get u square both sides, squared, so we now have 1 over 3u squared plus 2, minus, sorry, because I'm always making mistake, minus 2u plus 1 is equal to c1 squared x squared. Yes. Then at this moment we can multiply this, both sides by 3, negative 3u squared minus 2u plus 1. So we will get here on this side, we will get 1 is equal to negative 3 c1 squared x squared, u squared minus 2 c1 squared x squared u plus c1 squared x squared. So we can just let c2 equals to our c1 squared. So we have now 1 is equals to negative 3 c2 x squared u squared minus 2c2x squared u minus c2x squared plus, so, and we will transfer 1 to the other side, so we will have 0 is equals to negative 3c2x squared u squared minus 2c2x squared u plus c2x squared minus 1. And we can rewrite this equation by multiplying both sides by negative 1, so we will have 0 is equals to 3c squared x squared u squared plus 2c2x squared u minus c2x squared plus 1. And we, as you notice, we have a quadratic equation here. If we will let a is equals to r c squared 3c squared x squared and b equals to r 3c2x squared and c is equals to r c2x squared plus 1, negative c2x squared plus 1. So as you recall, we have our quadratic formula, which is equals to y equals negative b plus minus square root of b squared minus 4ac over 2a. So we will have now, so we just substitute the values since we're getting 4u, so we have u equals our b is here negative 2c2 x squared plus minus square root of 2c2 x squared minus 4 times our a, which is 3c2 x squared, and our c times our c, negative c2x squared plus 1. Then we over this with 2a, which is our a is 3c2x squared. And now we are now ready to solve our quadratic equation. Solving for quadratic equation, we have Now we have the value of u. We will substitute back from our substitution. U is equals to ux, so we have y u, so we have u equals to y over x. So we'll substitute this y over x here to u, so we have multiplying both sides with x, we got oh, sorry. Still have a squared here. Sorry for that. Is correct. So we have solutions in this problem, which is y equals negative 1/3 x plus square root of 4c2 squared x squared minus 3c2 over 3c2. This is the first solution, and the second solution is y equals negative 1/3 x minus square root of 4c2 x squared c2 squared minus 3c2 over 3c2. Now we have the problem. A unit particle moves along the x-axis in a resisting medium, and resistance is proportional to the velocity. If the particle starts from the position x equals x sub o with velocity v sub o, find the limiting position approached by the particle. Take negative kv with k greater than 0 as the force of resistance. So since this problem is a modeling problem, so we can just, so first we have to identify the variables. So we will let x equals to the position of the particle at time t, and then velocity as the v as the velocity, and k and m is the mass. And what we are going to find here is the limiting position approached by the particle. So first we have to find an equation for our velocity before we can find the equation for our position. So in this case, the force on the body is resistive and is proportional to its speed. So the equation of motion is mdv over dt equals negative kv. Mass dv over dt here is the acceleration. As you can recall in physics, acceleration is just the derivative of velocity, and negative kv is our resistance force, which is given in the problem. So now we have created a separable differential equation, so we can just evaluate this. So first we can multiply both sides by dt and divide both sides by m and v. So we will have dv over v equals negative k m dt. So we can now evaluate both sides of the equation. So here I'll have to integrate this. So we have lmv equals to negative kmt plus c, where c is an arbitrary constant, and we can just write it this way for it to be easy. Negative, this will become ln of e to the negative kmt plus ln e to the c, and we'll let e to the power of c as our c1. So we will have ln v equals to ln e to the negative kmt plus our ln of c1. And as the properties of natural logarithms, we can combine these two terms as ln v is equal to ln of c1 e times e to the power of negative kmt. So we will have now v is equals to c1 e to the power of negative kmt. So now we now have the expression for velocity, but we have to find the value of c1 by using the velocity at time is equal 0 is v sub o, as what is given in the problem. So we have substitute it here. So we have the velocity equals to v sub o is equals to c1 times e to the power of negative km times t, where t is equal to 0 times 0. So this will become e to the power of 0, so it will become 1. So we have v sub o is equals to c1. And since we have now the value of our c1, which is v sub o, substitute it back to the expression of v. So we have v is equal to v sub o times e to the negative k over m times t. And this is now our final equation for our final expression for v. But the solution of our problem does not end here, because we still have to find the limiting position approached by the particle. When we said position, we need to find for x. So we need to express this expression in terms of x. Recall that we have v is equal to dx over dt, right? Dx over dt, change in position at time t. So now we will substitute this value to our v in this equation. So we have dx over dt is equal to v sub o e to the negative kmt, and this is a separable differential equation, so you can just multiply both sides by dt. So we will get dx is equals to v sub o times e to the negative k t dt. Then integrating both sides to get x. we have x is equals to v sub o. It will become negative v sub o times, because you will multiply with negative km times e to the negative km t plus c2, and c2 is an arbitrary constant. So now, in order to complete the expression of x, we need to find again the c2. And on our problem, it is given that the position at v sub o, where it is the value of velocity at time equals to 0, is x is equals to x sub o. So we will just so at time equals to 0, x is equals x sub o. So x sub o is equals to, you will just substitute it here, is equals to negative v sub o k over m times e to the negative km t plus c2. But then we have time equals to 0, so we have x sub o equals negative vo km e to the power of negative km times 0 plus c2. So e to the power of 0 will become 1, so we have x sub o equals negative vo times k over m plus c2. So in order to get c2, we have c2 is equals to x sub o, we transfer this, plus v sub o times k over m. So now that we have the value of c2, we can now substitute this to our expression of x, which is this. So we have x is equals negative v sub o k, we are here, km times e to the negative km t plus x sub o plus v sub o times k over m. Then, since we are to find the limiting position, so we will the limiting position approached by the particle. So it means that the position of the particle as t approaches to infinity. So in this case, we will just get the limit of it. So we will have the limit of x as t approaches to positive infinity equals to limit as t approaches to positive infinity of negative v sub o k e to the power of k over m t over m plus x sub o plus v sub o k over m. So its limit is negative v sub o k e for negative k m times positive infinity over m plus x sub o plus v sub o k over m. So now we have here this will become negative v sub o k over m, and the e here will become e to the negative infinity plus x sub o plus v sub o k times m. Now we have e to the power of negative infinity is 1 over e to the infinity, which means it will become 0 times 1 over e to the positive infinity plus x sub o plus v sub o k over m. So this e here will become 0, so negative e of k m times 0 equals 0. So we have the remaining equation x sub o plus v sub o k over m, and that is our x as t approaches positive infinity. So our final answer here, and now we have the answer of limit of x as t approaches infinity, which is x sub o plus v o k m. So our final answer here is x is equals to x sub o plus v sub o k over m is the limiting position.